Hello everyone, myself Devashish Das, Assistant Professor of Electronics Communication Engineering Department of Greater Kolkata College of Engineering and Management. In this video, we are going to study about the different topics of analog electronics and its applications, how the analog electronics apply in our different fields of electronics. In this video we are going to study about it, different circuits and its part we are explaining one by one in this topic. Analog Electronics 1. This course is mainly for diploma students of electronics and telecommunication engineering of third semester. The paper code is PTCE AE1S3. Welcome to another sessions of my video lecture. In this session we will discuss about the semiconductor formation. That means how the semiconductor is being formed and what are the types of material is used. In this session we will discuss about it. In this session we will discuss the extrinsic semiconductors, the p-type semiconductor, n-type semiconductor, difference between p-type and n-type semiconductor, and the conduction in the semiconductor. That means what are the various types of conduction occur in the semiconductor, that will be discussed in this session. Let's begin. First, what is extrinsic semiconductor? When we add an impurity to a semiconductor to increase the charge carrier, then it becomes an extrinsic semiconductor. In extrinsic semiconductor, without breaking the covalent bond, we can increase the charge carrier. That means we are adding impurity to a pure semiconductor or the intrinsic semiconductor to change its conductivity. So the octet rule, this is the important rule in the semiconductor. The octet rule states the elements gain or lose electron to attain an electron configurations of nearest to the noble gases. The noble gases are the most stable elements because they have a full valence electron shell. All elements want to be stable like the noble gases. That is why there are ions. If an element give up or gain electron, it has better chance of being stable like a noble gases. The octet rule is the very important rule in the semiconductors. The octet rule states the stability of the atoms. That means every atoms want to be or try to be stable itself by allowing the 8 electron on its outermost orbit. We will discuss it. Another thing is the covalent bond. Covalent bond is nothing but the sharing of electrons. That means here you can see the two examples. The first example consists of fluorine atom which has 7 electrons in its outer shell. The two fluorine atoms combined and share 1 electron to each other and make a octet in the outermost orbit and make it stable. So the two fluorine atom, by sharing 1 electron each, they made a octet in the outermost shell and they are stable in nature. It is the example of the covalent bond. Covalent bond is the sharing of electron. So we can see another example. It is the water molecule, the H2O. Here we can see 2 hydrogen atoms which is 1 electron each, and they share 1 electron with another oxygen associated with oxygens. So the outer cells of the hydrogens become 2 and the outer cell of the oxygen, the amount of electron become 8. In this way they are sharing electrons in the outermost cell and form the covalent bond and being stabilized itself. These are the two examples of covalent bond. We can see how these covalent bonds are applied in our semiconductors. We'll discuss one by one. So there are two types of adding impurities to a pure semiconductor. One is n-type semiconductor, another is p-type semiconductor. In the n-type semiconductor, elements with 5 valence electrons are introduced as impurity to a pure silicon known as the n-type doping. Elements with 3 valence electrons are introduced as impurity to a pure silicon is known as p-type doping. Here we can see in n-type phosphorus impurity is added to a pure silicon structure where the 4 electrons are being shared and 1 electron is not shared and it's free. Similarly, in a p-type semiconductor, a boron atom is injected or it is placed in the silicon structure where the 3 atoms are shared, 3 electrons are shared, but 1 electron is vacant. So it is the vacant of the electron, that means it is whole. We will discuss it one by one. So in this structure, or it is the periodic table, we can see the silicon and germanium is the pure semiconductor or intrinsic semiconductor. It is group 4 element where we add group 3 or group 5 elements to make p-type or n-type semiconductors. These are the impurities which are added with the group 4 element or the pure semiconductor, and we can create p-type or n-type semiconductor. The group 3 elements, boron, aluminum, gallium, indium, these are the impurities added to the pure semiconductor, silicon or germanium, to make p-type semiconductor. And we added group 5 element like phosphorus, arsenic, antimony with the silicon and germanium to make n-type material or n-type semiconductor. We will discuss it, but this chart is very helpful to understanding the semiconductors. So the extrinsic semiconductors, that means we added impurities. In the first example we can see the antimony, which is group 5 element. Here the 4 electrons are being shared with the associated silicon atoms and 1 electron is not shared with the associated silicons, so the electrons is free and it's moved to the conduction band. So in this way we can see how the electrons is free by adding of pentavalent impurities, where we can see in the boron, adding of boron, it is the valency of 3, so the 3 electrons are shared with the silicon atoms associated with it, and there is a 1 vacancy, that means it is the hole is created in the silicon boron structure. So here we now come with the comparison between the intrinsic, that means pure semiconductor, and the extrinsic, that means it's non-pure or the doped or impure semiconductor. First, it is for the intrinsic semiconductor, it is the pure form of the semiconductor, and in extrinsic semiconductor it's formed by adding trivalent or pentavalent impurity to a pure semiconductors. In case of intrinsic semiconductors, hole and electrons are equal, and in case of extrinsic semiconductors, number of holes are more in p type and number of electrons are more in n type. For intrinsic semiconductor, Fermi level lies in between valence band and conduction band, and in case of extrinsic semiconductor, the Fermi level lies near valence band in case of p-type semiconductor and near to the conduction band in case of n-type semiconductor. For the intrinsic semiconductor, the ratio of majority and the minority carrier is unit, and for the extrinsic semiconductor, the ratio of majority and minority carrier are equal. So this is the comparison between the intrinsic semiconductor and the extrinsic semiconductor. So we can see a chart of the intrinsic semiconductor and the extrinsic semiconductor. For the intrinsic semiconductor, it is the pure semiconductor, the silicon and germanium, where the number of electrons and number of holes are equal. And for the extrinsic semiconductors, it is classified into two parts. One is n-type semiconductor and one is p-type semiconductor. These are the impurity added to get the n-type semiconductor with the pure semiconductors, the phosphorus, arsenic, antimony, etc. In case of n-type semiconductors, the number of electrons is more than the number of holes, and in case of p-type semiconductors, we added the trivalent impurities like gallium, boron, indium, aluminum, etc. to get the p-type semiconductor. In case of p-type semiconductor, we can see the number of holes is much greater than the number of electrons. So this is the another comparison, we can find it out. For n-type semiconductors, when we add pentavalent impurity to a pure semiconductor, we can get a n-type semiconductor. Arsenic is one of the impurity which is being applied to the pure semiconductor, or it is the dopant which is applied to a pure semiconductor, silicon or germanium, to get a n-type semiconductor. The n-type semiconductor, arsenic atom has a 5 valence electrons. 5th electron is superfluous, that means it's excess because the free electron and the enters into the conduction band. The electron is get free and it's moved into the conduction band. The 4 of them are associated with the silicons, but the 1 electron is non-attached and it's moved to the conduction band and it becomes a free electron. Therefore, the pentavalent impurities donates 1 electron and becomes positive donor ion. Pentavalent impurity known as the donor. So here is the example. You can see the antimony is the, here we take a antimony as an example, is associated and or it shared the electron with the side by side silicon atoms and form a covalent bond, and 1 electron is free and it moved to the conduction band of the semiconductors. So in this way the conductivity of the semiconductor is changed. More we dope the antimony, Sb is the antimony, more we dope the impurity of the antimony, more we get the free electron and the conductivity is going to increase. In this way, with the help of doping or the control doping, we can control the conductivity of the semiconductor. That is the beauty of the semiconductor or extrinsic semiconductor. Now we come to the p-type semiconductor. When we add trivalent impurity to a pure semiconductor, we get p-type semiconductor. Gallium is one of the p-type impurity or trivalent impurity which is added to a silicon or germanium to get a p-type semiconductor. Gallium atom has 3 valence electron. It make covalent bonds with adjacent 3 electrons of silicon atom. There is a deficiency of one covalent bond and creates a hole. Therefore, trivalent impurity accept 1 electrons and become negative acceptor ion. Trivalent impurity known as acceptor. In adding to this, some of covalent bond breaks due to temperature and the electron hole pairs are generated. Holes are majority carrier, the holes are the majority carrier and the electrons are the minority carriers. We will explain it with the help of this picture. Here we take a boron as a trivalent impurity where the 3 electrons form a covalent bond with the silicon atoms, but there is one vacancy of the covalent bond and which forms the hole. So in this way, or we can say the hole is the positive charge where it is the deficiency of electron. If the electron is negative charge, so that if there is a deficiency of electron, so the hole is become a positive charge and it take part in the conductivity of the p-type semiconductor. And in this way, if we add more boron atom in the silicon structure, we can get more hole and the conductivity is also increased in this way. So this is the example of a p-type semiconductor. We add the boron as an impurity in the silicon structure and we can change the conductivity of this silicon semiconductor or the p-type semiconductor. In this picture we can see the difference between a p-type semiconductor and the n-type semiconductors. For p-type semiconductors, the electrons are the minority carrier where the holes are the majority carrier, and in case of n-type semiconductors, the electrons are the majority carrier and hole are the minority carriers. So here you can see the comparison between the n-type semiconductor and p-type semiconductors. For n-type semiconductors, the pentavalent impurities are added. For the p-type semiconductors, trivalent impurities are added. For n-type semiconductors, majority carriers are electrons. For p-type semiconductors, majority carriers are hole. For n-type semiconductors, the minority carriers are holes. For p-type semiconductors, the minority carriers are electrons. For n-type semiconductors, the Fermi level is near to the conduction band, and for p-type semiconductors, the Fermi level is near to the valence band. So now we discuss the conduction in the semiconductors. What are the conduction take place? There are 2 types of conduction take place in the semiconductor. First is drift process, another is diffusion process. We'll discuss it one by one. First comes the drift process. Electrons move from external circuits and is conduction band of the semiconductors. The hole moves in the valence band of the semiconductor. It is the drift process. Drift process is mainly occurred due to applied of the external field or the external voltage. Here you can see the external voltage is applied. With the help of this external voltage, the drift process occurs. Now we take some mathematical expression of the drift process and we can plot the drift current. What is drift current? We'll explain. So here N is the number of charges E per unit volume, electron per volume. Q is the total charges. So A is the area. You can see A is the area of this cylinder. It is a cylindrical conductor. So A is the cylinder area of the cylinder, and D is the distance. So A into D is the volume of this part. So this A into D, AD, A is the area and D is the distance of this part. So A into D is the volume of this portion. Now the total number of charges is equal to the number of electrons, which is N, and E is the electron charge. So we can get the total charge of this portion of the conductor. This is the mobile charge in the length of D of the conductor. So T is the time for the charge to move from this part to this. This is the D, unit D. So the time taken to move a charge from this portion to this is the time T. If Vd is the average velocity of the charge, then we can find the time T equal to D by Vd. Vd is the average charge velocity. So I is the current. This is the well-known formula where you can find the current. It is the rate of charge flowing with unit time. So Q by T is the I. So we just put the value of Q and T, and by solving this equation we can get the drift current, which is N into E into A into Vd. Vd is the average velocity. So in this way we can find out the drift current. Now there is another current which is known as the diffusion current or the diffusion process. Moving of electrons from higher concentration gradient to the lower concentration gradient is known as the diffusion process. We have to keep in mind, for diffusion process there should be a concentration gradient. If there is no concentration gradient, there will be no diffusion. So to make flow of diffusion current, there should be some concentration gradient. This is the main important thing which you have to keep in mind. So we can just see the expressions of the diffusion current. So the diffusion current within a semiconductor consists of holes and the electron component. So here we can see it is the hole component diffusion current. It is the concentration gradient, and in this section we can find the diffusion current of the electrons. So the combinations of these two is give us the total diffusion current. So the total current flow in a semiconductor is the sum of drift current and the diffusion current. So it is the combined efforts of two, the drift current and diffusion current, which makes the current flow in the semiconductor. So here we can distinguish or the differentiates to diffusion current and the drift current. You can find out for diffusion current, the diffusion current occurs even though there is not an electric field applied to the semiconductor. For the drift current, electric field should be applied in the PN junction diode. For diffusion current, it's depend on the constants, the dP and dN. which is diffusion constants, and for the drift current it is dependent upon the permeability. It is the independent of permeability for the diffusion current, and drift current is the dependent on the permeability. So we can see the differentiation or the difference between the diffusion current and the drift current in this chart. So that's all today. Thank you. Thank you for watching. If you have any queries, you can contact to me. The contact number is given. The same number can be used as WhatsApp number. If you have any queries or doubt, you can call me or WhatsApp me to this number. Thank you very much.